And what I've noticed is because our class is in the afternoon, so our recording takes forever to process. And then the ones that are at 8 in the morning, they come back to me lickety split. So anyways, it's the afternoon. So everybody be zooming. Okay. So let's start with some review, and then we're going to get into chapter 9. If for some reason you have your hands on an older textbook, so an older edition, I noticed in the one that I'm kind of reading out of, it's chapter 8, so something happened there, but just look for networks, and that's it. So I must have added a section somewhere. Ashley. So review. We talked about changing bases, right? So going between, so we talked about binary enumeration systems. We talked about, yeah, exactly, Dermot, sorry. The WebAssign, there's an ebook there. Yeah. So it's gonna be chapter 9 in there that we're gonna do, but we'll do a review first and then we'll head into it. So binary enumeration systems, and then we talked about octal and hexadecimal systems, and moving back and forth between binary. So binary is kind of at the root of everything. So going between binary and octal, or binary and hexadecimal, or hexadecimal to binary, or octal to binary, right? And so we move through the binary, of course, because we're talking computers here. And so depending on, you know, the scenario, I don't know that much about these numeration systems. I just know how to move between them. So I don't really know when octal is used and when hexadecimal is used, but I feel like hex is colors or something. Anyways, might have made that up. I'm getting a nod, so that feels good. But anyways, so you guys probably know more about that. But for us, we just need to be able to move between the bases. So converting between binary and octal, and binary and hexadecimal. Octal for legs, hex for bugs. That's good. It sort of ties in with our Finding Nemo theme. We were just gonna watch Finding Nemo for our class. Sounds good. That's not what I was saying, Niall. No. Is it Dory or Dora? Dora the Explorer and Finding Dory. I never can keep them straight. Anyways, Dory's my favorite. You know you can get me off track with kids' movies. And I haven't even seen that many. I'm not like a connoisseur or anything, but they are really funny. Will the Krill is in, which one is Will the Krill in? Madagascar, I think. He had some funny ones. Kung Fu Panda. I have not seen Kung Fu Panda, but I'll put it on the list. All right. I guess I should focus. So we moved between binary and octal, octal and binary, hexadecimal, binary. We went back and forth. Remember the shortcuts, right? We group in 3s for octal and 4s for hexadecimal. So group in 3, I should write 3s. Group in 3s for octal and 4s for hexadecimal. So what I'm going to do is I am going to steal the list that we made because we already did the conversions last day. Now, where is it? Here it is. Okay. Aha. This is the one that I'm going to steal. Copy, because I can. So here, from 0 to 7, right? We have just leading zeros here. And so what I'm going to do is, I did not do a very good job here, but what I'm going to do is I'm just going to slice off that leading 0. And this is to octal, right? They're the same number, but in base 8, if you're moving to and from base 8, then 0, 1, 0 base 2 is going to be 2 base 8, right? So octal is base 8. To octal, and I'll say base 8. Okay. So we had a list of examples that we were going to work through, and we did a lot of them, but I'm going to steal the rest of them to finish here. And so we're going to do 3 and 4. Copy pasta. I'll scoot these down. Whee! Okay. But 10 and 11 binary, when I use the method we did in class. 1, 0 plus 1, 1, base 2, didn't work. Oh, and I guess I should add that to the list of stuff we did. We did binary addition and multiplication. So you're doing 1, 0, 1, 1. And I'm going over a page break, so I'm just going to bump them down. You don't get 1 and then 1, 0 base 2. If there's one giving you grief, Ashley, can I do the whole thing of this? Oh, is it 1, 0 times 1, 1? Or is it just adding? Because if you're just adding, then the key is to remember that, so then you just add like you would normally. So 0 plus 1 is 1, but 1 plus 1 makes 1, 0. So you technically have this, you kind of carry the 1, 0 and bring it down. Does that kind of do it? It's different if you're multiplying. Okay, cool. That's allowed to misread. Okay, I'm gonna delete that. forget about it. Cool. So now if I'm converting to hexadecimal, that's base 16. So now I'm grouping in 4s, right? And so here, what I want to do, and I'm gonna just kind of make some room here. It's from last day, so I can do whatever I want, I guess. Don't worry. You should have these in your notes already, so that's why I'm not too worried about it. So if we're going from base 2 to hexadecimal, right, then we can use that shortcut of grouping by 3s. 4s. Yeah, this is from last class. This example is from last class. You wish it was our last class. Yeah. We did go over Ascii values, and I even put in a table of some of the Ascii codes. Let's see here. Here are some Ascii codes. You might have to Google your way to some other ones if you need them, right? Like I think it asks you to spell some stuff in Ascii. So those, you might not have all the ones that you need. You could figure it out, but yeah, so we did go over them. They're in the notes from last day. All right, so we're gonna group in groups of 4 for hexadecimal. Groups of 4. So starting from the decimal, in this case, that's to the very right. So now here we go. 1, 2, 3, 4. Oop. 1, 2, 3, 4. Hey, nice. Solid 4. What happens if we don't have a full 4? Well, we have to add leading zeros or trailing zeros, depending on which side of the decimal we're on, right? And so now we can just refer to our table up here. We have to find 1001. 1001 is going to make a 9 base 16. So I can replace this with 9. And then 0, 1, 1 is going to be 7. Okay. So this is going to be 97 base. And I'll write hex so I don't have to write 16. Right, hexadecimal is base 16. So let me put this one, move it up 1. Doing the same thing again, right? There's no decimal here, so I start from the very right. Yep, right. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Leaving room for a leading 0. So again, right, I had to make this a group of 4, but that's okay. So 0, 1, 1, 1 is, I already know that it's 7. 0, 1, 1, 1, that's 7 again. Hey, too easy. 7 again. So this is going to be 7, 7, 7 hex. I'll put this on the new page. Bink. And now, right, we start at the decimal. The decimal translates, and I think I forgot to bring it in sometimes last day, so I'm gonna really try to stay on top of that, because if I'm having troubles, you're probably gonna have the same issue, right? Or maybe not. But I feel like it's likely. So starting at the decimal, right, I can make a group of 4. Zeros to the left Oh yeah, so whichever doesn't alter your number, right? If you put zeros here, it actually alters your number, right? 10 is different from 100, whereas 0, 1, 0 is not different from 10, right? So whichever way doesn't alter your number, whereas if you're over here, if you have 0.5 versus 0.50, they're the same. So it depends on which side you're moving to. Leading zeros, trailing zeros, but you don't want to alter the number. So then here from the decimal 0, 1, 1, 0, groups of 4, all right. So now I've got 1, 0, 0, 0. I can translate this, but I already know that I'll probably forget the decimal, so I'm going to add it in right away. So I don't forget it. Know your weaknesses. 1, 0, 1, 1 is B, capital B. 0, 1, 1, 0 is a 6, so point B, 0.6, and then 1, 0, 0, 0 is 8. So we have B 0.68 hex. Weird, but fun. Right. I'll move this up here. If we have to do the reverse, right? Well, now, just like we were saying, okay, I'm going to make groups of the binaries in groups of 4, and I'm going to replace them with the hexadecimal. Now I'm going to take the hexadecimal and I'm going to just expand it out to the binary. So there's going to be 4 digits in binary. So here we go. 4 I can translate to 0, 1, 0, 0. And you might find it helpful to leave a little bit of a space so that you can see your own groupings of 4, right? And so C is 12, which is 1, 1, 0, 0. Okay. So now I have 1, 1, 0, 0. And then 1 is 0, 0, 0, 1. Oh, it's lagging a bit today. Okay. 0, so 3 zeros followed by a 1. These 2. Okay. So notice that I'm kind of keeping my groupings just in case I have to go back and check my work. Seeing all these zeros and ones, it can get kind of messy, right? You don't need this leading 0. It doesn't hurt to have it there, but you don't need to have it. Or 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, base 2, if you prefer. Because I forgot a 0. Keeping me honest. It's good. Go me. Here I am. Groups of 4, groups of 4. Here's 3. That's good. All right. Last one. So really all we're doing is we're just translating this. Yeah, don't test my ability to count to 4. Do not test me. Hey, weird things happen. Another one. A we know is 1, 0, 1, 0. So when I'm dealing with the letters, there's no risk of me ruining it because I have to have 4. Starts with a 1. There's actually I think the next section does talk about finger counting. We're not doing that section, but it does talk about our first calculator. Hands. So I think it's A that I want. 1 0 1 0. 1 0 1 0, and C 1 1 0 0. Ta-da! This is going to be kind of weird because it's part of the review. We also did, I should have squeezed it in upstairs in the notes. We also did binary addition and multiplication. Yeah, I'll take all your names in binary. What are you going to do if you have a letter more than F? What you going to do? You have to cycle back. F plus F. Yeah, so you would cycle back through, just like 0s and 1s in binary, right? You would cycle, so you would cycle through modular arithmetic. Anyways, doesn't matter, we're not doing that, but that's what you would do. So, where are we at for, okay. That's gonna have to be the end of our review. And now we are going to talk about networks. Not networking, networks. But they obviously are definitely related. Obviously, definitely. So let's see here. I put it on a fresh page. Ops. Let's put it on a fresh page here. So chapter 9 is going to be, we're just going to do 2 sections in chapter 9, hopefully 1 per day, but I mean, they're pretty meaty, so we'll see how we do, but pretty fun. So networks and graph theory. And I guess I should write a capital G. It's the title of our chapter. And so we're only going to do 9.1 and 9.2, but there is more if you're interested. One of the problems that we're going to talk about recently had an improved solution. So it's one of those problems that people have been working on for a long time. And so it very recently had an improved solution. So it's not, you know, the go-to solution, but it's the best solution so far. So pretty cool. I posted a link to that on Moodle in case you're interested. But before we talk about that, let's start 9.1 is on Euler circuits. So Euler is a famous mathematician. It looks like Euler, but we say Euler. Essentially. Go Oilers. I opted out of the Let's Go Oilers license plate, but maybe I should have gone for it. Considering I don't really watch hockey, I felt like I was putting myself out there too much. Okay, so Euler is a famous was a long time ago, famous mathematician. And so he presented a solution to the first problem that we're going to solve, and then we're going to look at another type of problem. So Euler circuits, oops, I almost wanted to write Triscuits. Euler circuits and Hamiltonian cycles. And Hamiltonian cycles. So we'll start with yes, of course, Shakespeare. Yeah, not a sponsor yet. So Euler circuits and Hamiltonian cycles sounds weird. It is a little bit, but I mean, we kind of have to deal with this stuff. We don't name it though, but they're just little problems that we have to solve. So there are two different types of problems. We'll start with Euler circuits and then we'll move on to Hamiltonian cycles. So the first problem, and I posted, so just so you know where it is, on Moodle, the Moodle caboodle. Here, I posted the link to the traveling salesman problem, which has the kind of the improved solution, and then also just the figures that I'm going to be using. You can probably draw these out, but I just didn't want to risk it. Whenever I copy stuff out, it seems to just go wrong. So anyways, the figures are there if you want them. So the first one that we're going to steal here, copy. Hey. Okay. So the Kevinsburg Bridges, this is a problem, and it's kind of like a classical problem that we have. Hey, why is it all? Looks like it's off tilt, but it's not. The problem is, so here's a city, right? And there are 7 bridges connecting 1, 2, 3, 4 different landmasses. So yeah, don't copy this picture out, don't worry about it. But I'm presenting the problem. So that's why I posted it on Moodle. This is the one that I can't recreate. But you could just do 1 landmass, 2 land, 3, 4, and then connect them with some bridges, right? So this is a classic problem. And so the problem is, all right, you have to start somewhere, anywhere, and you have to cross each bridge once, but only once. And then you have to end up at the same location where you started, okay? So here's the problem. And I'll move this up a little bit, bink. The problem. Start anywhere. Okay. and cross all bridges exactly once and finish where you started. Okay. I'm going to save you a lot of heartache and tell you it can't be done. Okay, so, but what we're going to develop is a solution for why it can't be done. So an argument for, well, because it has these properties, it can't be done. Okay. I know, everyone's so sad about it. I was too. So here we go. You can try it. I mean, kind of try it. So you start here, and it doesn't really matter where on this blob, right? So if you kind of ignore all the streets and stuff and just kind of boil it down to 1 blob, 2 blob, 3 blob, 4 blobs, right? That'll make it a lot easier, because once you've crossed over to this blob, you can easily walk from bridge 1 to bridge 2, right? And so blobs we actually call vertices, but we can think of them as blobs, right? And so what we're going to do is we're just going to develop kind of the thinking around how do we solve this problem, and then I'll give you the solution. But yeah, I was pretty bummed when I found out it can't be done. So I'm like, okay, I'll start here, and then I'll go here, and then I'll go here, here, back here. You can see I already ran into some trouble here, but then I can't get back. Anyways, so, all right. The solution we will discuss, and of course, others have presented other solutions, but the one that we're going to discuss and kind of the most widely accepted is, of course, the one that Euler came up with. So the solution we will discuss was first developed by Euler, and build another bridge. Yeah, that would be a solution. You'd have to wonder, I guess we could figure out where you would have to build the bridge to make it work. That's a good solution. Not to this problem, but to the problem. Yeah. So it was first developed by Euler, and it led to the development, and it led to the development kind of a history lesson here. Yeah, Euler had his fingers on the pulse, so to speak. If it was even remotely related, yeah, he had something to do with it. Yeah. So, and it led to the development of 2 major topics in geometry. The first one is networks, which is what we're talking about now. And the second is topology. We're not going to do any topology, but might be fun to look into in your spare time. So the first thing that we said was, okay, well, how about we just boil it down to blobs, right? Instead of blobs, he probably didn't say that. In fact, bet money that he didn't say that. Especially because he was Swiss. blobs. So he first represented land areas as blobs. Sounds French, but how do you say blobs in German? Swiss German. I don't know. Who knows? Maybe someone speaks German here. I don't know. Blobs. So he first represented land areas as vertices. Land areas as vertices, right? Or nodes, which, yeah. We'll assume you speak English, but then what else do we have going on here? So I know what we can draw on. Big Latin, out of my depth. It's pretty good though. So the first thing he did was boil down each landmass to a blob. I only took Japanese 9, and it was really fun, but I don't remember anything. But it was really fun. I know I'm the same for French, Zach. I can read it fine. But then when it comes time to order something in a restaurant, I'm mute. So he boiled it down to blobs. And then, so here, let's just highlight that these are kind of vertices or nodes. So there's a lot of terminology that's going to come our way here, just so we're able to talk about these networks. And so, and the bridges were, so he first represented land areas as vertices / nodes, and the bridges by arcs / line segments, Okay. Sometimes we call them edges, and we will call them edges later, so that's why I'm highlighting that. So there's a lot of different words for the same thing. Connecting the vertices. Okay, so what I'm gonna do, right, is I'm just gonna study this picture here, and I mean, I could cheat and call it, and kind of write over here and then bring it down, but I'm not gonna do that. So we'll have one vertex here on this blob, another one here in the island, and then another one here, and then another one here, and then we'll connect them with the bridges. So what we have is we have something like, we'll do A, hey, this isn't the same graph. When did I when did I want to do that? So we have A, B, C, D. Oh, it is the same graph. Never mind. So C is the island, okay? And from the island, I'm really kind of, what I'm gonna do, I'm just gonna copy this little guy here and make it really small so I can copy it into my, so we'll call this A, B, C, D. Okay. A has a bridge going from, and you know what? Yep, let's do it. A to C, A to C, right? So from this blob, I've got 2 bridges going down to C, to the island, okay? And then from A to B, I have 1 bridge. Okay. From C to B, I have 1 bridge. From B to D, I have 1 bridge. And then from C to D, I have 2 bridges. I'll curve that one out so we can see it. Hey, fun shape. It's like a cone got smushed, which I would never be able to draw if I was trying to draw it, but here we are. So hopefully this is what I want. Let me do 1, 2, 3. Good, okay. Shapes are fun. Okay, so here, this is a boiled down version of our potential paths, right? So you're allowed to start at any vertex, and that's what makes it hard, right? To figure out where you should be going. I already told you we can't solve this problem, but looking at this, right, we've got some vertices, right? So here, these are vertices. Okay. I'll do some light blue for these are called the edges or the arcs or the line segments. So these are the edges / arcs, if you prefer. And then the newest terminology is going to be, okay, we're going to call each portion that's been separated out is called a region. But one thing that we're going to remember is that outside here, right, when I plop down this kind of grid or this network on a map, right, I'm separating everything in here from the outside, so the outside is also a region. And for me, that's not something that comes immediately, so that's why I'm highlighting it. So here, I'll just kind of show that these are regions. Okay. Just some terminology, right? And note, the outside is also a region. Oops. Okay. Okay. So for a graph, so we can call this a network or a graph. Okay. And what color haven't I used yet? This whole thing. Called a network or a graph, confusingly enough. Well, it is a graph, right? Usually we think of kind of infographics, histograms, pie charts, that kind of thing for graphs, but it's also a graph that we're looking at here. So a graph like this is connected if everything has a connection. So we say a graph is connected if there is at least one path, between each pair of vertices, And that's a definition of connected, which we'll just kind of use loosey-goosey now. Okay. So let's talk about Euler circuits. Now I'm introducing this a little bit ahead of time, but I think it's good to kind of have a handle on it. Okay, so an Euler circuit, and this is a definition of an Euler circuit. We're going to begin at some vertex, yeah, and then we're going to travel on each edge, right, or line segment or arc, whatever you want to call it, exactly once, and then return to the same vertex. So we begin at some vertex, any vertex. Hey, sounds a lot like the problem that we're looking at, right? And yeah, of course. So we begin at some vertex. Travel on each edge exactly once. And then return to the starting vertex. And then return to the starting vertex. Okay. So the Kevinsburg problem is really just, is this an Euler circuit, yes or no? Right, because our goal was to start somewhere and cross each bridge exactly once. The bridges are the edges, right? And then return to the starting vertex. So really, we can rephrase the Kevinsburg problem as, does this network have an Euler circuit? Does this network have an Euler circuit? Oops. Oh. Okay. So from that handout that I posted on Moodle, what we're going to do is we're just going to get familiar and we're going to count vertices, we're going to count edges, and we're going to count regions. So count, oh, this is an example, I guess. Example 1. Count the edges, the vertices, and regions of the following. oops, copy. Not bad. These are nice and easy. But often what happens is to develop this type of network, right, or graph, the problem can be quite complex, right? We would have to boil it down to just 3 vertices and then find the edges that connect them, right? And so we're just going to start and look at, you know, just the basic shapes, right, or the basic graphs. But then a lot of word problems will have you develop the graph and then solve the problem, right? A little bit harder. So for A, right, if we're counting the edges, and I'll make a little bit of room here. So we're counting the number of edges, we're counting the number of vertices, and the regions. Okay. In part A, right, or A, well, it looks like I have 3 edges and 3 vertices and 1, 2 regions, right? That's what caught me off guard, is that the outside is also a region, which makes sense because I'm blocking off this other region. So I've got 3 and 3 and 2. Okay. How about B? Well, now I've got 1, 2, 3, 4 edges and 3 vertices. 4, oops, that doesn't look like 3. And how many regions? Looks like I have 3 regions. C? Well, now I still have 3 vertices, so I'll start there, but 1, 2, 3, 4, 5 edges or arcs. And 1, 2, 3, 4 regions. D, I've got 4 edges and 4 vertices and 2 regions. E, again, I have 4 vertices, so I'll start there, and then I've got 1, 2, 3, 4, 5 edges and 3 regions. And finally, F, I've got 4 vertices still, right? But now I have 1, 2, 3, 4, 5, 6 edges. 6 edges, 4 vertices, and I have 1, 2, 3, 4 regions. Yeah, so it depends on how you want to think about it. Yeah, so you could do the edges minus the vertices plus 2 is the number of regions, or notice that V plus R minus 2 is E, right? So there is that relationship, right? And because if you do V plus R is 5 minus 2 puts me at E, right? And so here I'm at 3, 3 plus 3 is 6 minus 2, puts me at 4. It's going to work out. Right? So there is that relationship, which we're not going to get into. I don't actually know. I'm assuming it's true all of the time, but I don't know. So could look it up, but I just didn't. So 3 and 4, 7 minus 2 is 5, 6 minus 2, 4, confirmed. Good. So there is a relationship here. there is a relationship that V plus R minus 2 equals E. But then I don't know, I'm assuming it is true all the time, but I'm not committing to anything. Michael's nodding his head. Looks like it's true all the time. Well, if Michael says so, I'll commit to it. Totally. Well, and patterns definitely help, right? So, because then we can kind of say, oh, okay, yeah. So, there is this relationship. Or V plus R plus E equals 2 minus E. There, I almost mucked it up. Okay. Good. So there's that relationship, but that's about as far as we're going to go. All right. Getting down to, we're sort of close to solving this problem. First thing we have to develop is this idea of traversability. So a network is traversable. Okay, so let's do, or can be traversable. A network is said to be traversable, oops, and this is definitely a definition. If it can be traced in one sweep without lifting the pencil from the paper and without tracing the same edge more than once. So in one sweep without lifting the pencil from the paper, and without tracing the same edge more than once. The same edge more than once. Vertices may be passed through more than once, right, to be traversable. Vertices may be passed through more than once. That was kind of a holdup for me because I didn't want to go through, so in the bridge problem, the Kevinsburg problem, I didn't want to pass through vertices more than once, but then you don't get anywhere, right? So we're allowed to pass through vertices more than once. It's the edges we're concerned with. So, all right. So that's what it means to be traversable. So now we need to develop more terminology and more. But it's all pretty standard stuff, right? So the degree of a vertex is how many edges meet at that vertex, right? And so the degree of a vertex is the number of edges, that meet at that vertex. That meet at that vertex. Okay. And then what we're going to do is we're going to be able to classify a vertex as either even or odd, depending on what the degree is, right? And that's going to be really useful for solving this problem. We can classify each vertex as even or odd, depending on its degree. And then just as a little fun fact, right? But it kind of, if you map enough of them out, it'll be obvious, right? But the sum of the degrees, right? So remember, the degree of the vertex is the number of edges that meet at the vertex. So the sum of the degrees is always going to be twice the number of edges, right? Because one edge goes to two vertices, right? So here, let's add a little fun fact. The sum of the degrees of the vertices will always be twice the number of edges. Will always be twice the number of edges. Sweet. Okay. So if we kind of think about, okay, so if we have a vertex here and it has 1, 2, 3 edges, right? Then here the degree is odd, right? Degree is 3, which means it's odd. Okay. And if a vertex is odd, then it has to be either a starting point or an end point. Okay. So if a vertex is odd, it must be a starting or an end point. Must be a starting or an end point. If it's, so if we have these odd vertices, right, and an odd vertex has to be either a starting or an end point, we only have room for 2 odd vertices, right? So therefore, we can only have up to 2 odd vertices. Right. I should say to be traversable. For a graph to be traversable. And remember, traversable, going back here, right? If you can trace in one sweep without lifting your pencil and without tracing over the same edges more than once, okay? You're allowed to pass through vertices, right, more than once, but the edges you can only pass through once. So in order to even be a runner-up for traversable, right, we can only have 2 odd vertices. There's only room for 2 odd vertices. So here we go. So this, we're so close, so we're not gonna obviously prove any of this stuff. We're just gonna use it because it's way beyond our scope, presumably my scope. I don't know. I haven't looked at the proof. So definitely not something we're going to worry about, but it is something that we're going to use. So we state, and I'll say without proof, and I'll set it up as a table. So we'll talk about the number of odd vertices, whether it's traversable, and I'll move this over a bit. And the start and the end points. Okay. So we'll start with talking about if you have no odd vertices. And just as a rule, yes, it is traversable. And as far as your start point, you can start anywhere, and you can end, or you will end up at the starting point. Any and at the start. Sounds promising and sounds familiar, right? Has to be traversable. We only cross each edge once, and I have to start somewhere and end up back at the start. Right? Sounds like an Euler circuit, but if we have one odd vertex, then it is not traversable, right? Which means you're not going to have a start and an end point because we don't care if it's not traversable. Okay. So we have to keep track of all these different definitions, right? What does it mean to be traversable, starting and endpoints, vertices, etc. So if we have two odd vertices, remember we said we cap out at two odd vertices, and anything else is not going to be traversable because we won't be able to cover all our vertices. 2 is traversable, and you're going to start at the first odd vertex and you're going to end at the second odd vertex. So if you have two odd vertices, you'll start at one and you'll end up at the other. So you won't end up where you started, right? But you'll end up at the other odd vertex. And then for anything kind of 2 plus or plus 2, doesn't matter. It won't be traversable, so we don't have a start or an end point. Yeah. So we can use this to determine if something is traversable or not. So going back to the Kevinsburg problem, if we look at our little sketch that we made here, oh wow, I really did it up, huh? Okay, let's see if I can grab this. Copy. Okay. There. Clean it up a little bit. Okay. What if we have to talk about, so let's talk about each vertex, A, B, C, D. And let's talk about the degree. The degree of A, well, the degree is just how many arcs feeding into A. So 1, 2, 3. For B, same deal, 1, 2, 3. C, 1, 2, 3, 4, 5. Yowzas. 3, 5, and then 3. Notice that these are all odd, right? 3 and 5. And so because they're all odd, we have 4 odd vertices. So right away here, I know it's not going to be traversable. Okay. So here, we have 4 odd vertices. Okay. So since we have well, more than 0, but since we have 4 odd vertices, the graph or the network is not traversable, and therefore, whoa, what happened there? And therefore not an Euler circuit. Okay. Which brings us to Euler's circuit theorem. A theorem is something that we can just use. We assume that we can use it. It's been proven, so we just go ahead and use it. Just like we did without proof here, we can still go ahead and use this. It's been established. But here's the actual theorem. So Euler's circuit theorem. And I'll underline this because it's kind of a big deal. All right. Oh. Say when. More? A little bit more, or are you good? So what we said, right, is, okay, well, to be traversable, what does it mean to be traversable? Oh, a little bit more. How are we doing? Say when. Cool. All right. Well, so to be traversable, right, we had to start somewhere and we had to trace each of the edges once, but only once. We can go through the vertices as many times as we want, right, but not the edges. And then now the Euler circuit is that we are ending up at the starting point. So the only time that that happens, right, is if we have 0 odd vertices, which means all our vertices have to be even. And so that's what Euler established, is that, okay, if you have to start somewhere and end up at that start point and only cross each of the edges once, right, you can only have even vertices, right? And so what we're going to say is that every vertex, and I'll kind of keep it scroll down here, but every vertex on a graph with an Euler circuit, has an even degree, oops, has an even degree, right, which is what we established. We can't have any odd degrees. And conversely, hey, you had to write the converse, the inverse, the contrapositive, right? So, and conversely, wait, if in a connected graph, right? So we can't have something left out or just kind of flailing in the wind. So if in a connected graph, every vertex has an even degree, every vertex has an even degree, then the graph has an Euler circuit, right? So for an example, let's say example 2, which is on your handout here, copy. Example 2, we're just going to figure out, I want you to find an Euler circuit. First thing you're going to do, right, is, okay, well, here, I have to make sure that I have no odd vertices, right? Hey, 1, 2, 3, 4. For some reason, I was seeing only 3 of these edges. It's like, hey, it's odd. It doesn't work. Okay. But first thing we're going to do is we're just going to make sure, okay, so it seems like they have the degree listed, right? So 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Okay. So we're not going to be able to find an Euler circuit. It is traversable, right? But because of these two, A and F, so it is traversable, but not an Euler circuit, right? Because we have 2 odd vertices, right? So we can connect this thing. We can start somewhere and we can connect them. Well, we would have to start at an odd vertex, right? That's what we learned from that table that we just made. So we'd start at an odd vertex and then we would end up at the other odd vertex, right? But the one that I'm interested in is not this one either. Hey, what gives? I didn't actually look at this, I guess. 3, 3, 3, 3, not traversable. Maybe I should change the name of this example. Is it traversable? Is traversable? Not traversable. All right. Okay. So the Euler circuit is a special case of traversable, right? It has to be traversable with 0 odd vertices. Now, there are a couple of applications, right, or tons of applications actually of Euler circuits. Some of them were things like, okay, you're building a supermarket and everyone has to go through each of the aisles, and an Euler circuit would be you have to start at the same door that you're leaving out of, right, which is typical of stores, right? So if you're building this, you have to build an Euler circuit. What are some other ones? Same idea, the police patrol problem. So there are all these problems, but they all boil down to Euler circuits. Yes, so yeah, now all the stores are realizing who has an Euler circuit and who doesn't. Euler circuits, primo. Yeah, hey, this isn't an Euler circuit. I bet you so many people were saying that. Employees everywhere are putting those stickers down. Hey, it's not an Euler circuit. What are we supposed to do? That's really good. Yeah, so anyways, or you're some sort of security guard and you want to map your route so that you only have to go through each hallway once. Anyways, same idea. So the other type of problem that we could have is where we kind of flip the script and we say, okay, well now, right, for traversable and Euler circuits, I'm allowed to pass through vertices as many times as I want. It's the edges I'm concerned with. What if I flip it and say, okay, now I can only go through each vertex one time? And this is the problem that people have been working on for a really, really long time, still working on, because there's no set solution like we had here. So I'll say, consider a different type of problem. A different type of problem. The traveling salesman problem is so common and popular that it's just abbreviated TSP, and a lot of people will know what you mean, or at least in kind of these circles, that it's the traveling salesman problem. So the traveling salesman problem, and maybe you've heard of it, maybe you haven't, maybe it's Maybelline. Traveling salesperson problem. TSP. So imagine you're a traveling salesperson, or you're building an algorithm for Uber, or DNA sequencing. It all is going to be some variation of a traveling salesman problem. But you're a traveling salesman and you have to hit, I don't know, a handful of cities. But you don't want to pass through a city more than once. That would be inefficient, right? And so what you want to do is you want to pick a route where you minimize the time or the distance or the cost, or maybe a combination of these things, right? And so it's an optimization problem, and pretty interesting. So a salesperson starts at home and wants to visit several cities and wants to visit several cities without going through any city more than once. Without going through any city more than once. Oh, and then return to the starting city. That's a key. He has to go home. And then return to the starting city. similar, right? Similar to the Kevinsburg problem, right? The bridge problem, except the only difference is now we're focusing on the vertices, right? We can't go through the vertices more than once, but we have to start in the same place and end up back home, right? And so we have a fixed starting point and thus an end point for this problem. They would like to do it as efficiently as possible. They would like to do it as efficiently as possible, which could mean things like minimizing the distance, minimizing the cost, minimizing the time, minimize the distance, cost, time, etc. Or a combination of these things, right? So usually for our purposes, we only focus on something like, okay, you want to minimize the distance, okay? Or you want to minimize the cost, right? So this problem is basically we're just reversing the edges and the vertices in the Euler circuit. This is basically just reversing the edges and vertices in an Euler circuit. In fact, this in general, this type of scenario where we're limiting the number of times that we can go through each vertex to once, and then we can use the edges as often as we want, as long as we're kind of trying to minimize some aspect, right? The distance, the cost, or the time. We call this a Hamiltonian cycle. So a Hamiltonian cycle. So much history in these chapters. Visit each vertex exactly once and end at the starting vertex. So if we go back and we steal one of these examples, I'm going to steal this one. Make it a little bit bigger. So for example, can we find a Hamiltonian cycle for this network? We can go over an edge more than once though. Yes, edges are allowed. It's just the vertices. And then Hamiltonian cycle. It's a big deal. I guess it's this William Rowan Hamilton. There's a little blurb of him in the textbook. It's really fun. So I guess he was this child prodigy. So he read Greek, Hebrew, and Latin by the time he was 5. Holy smokes. So pretty cool. Pretty cool guy. I guess Irish. Anyways. William Rowan Hamilton. Yeah. Read. Yeah. By the age of 10, he knew over a dozen languages. He was appointed Professor of Astronomy and Royal Astronomer of Ireland at the age of 22. What have we done, huh? I'm going to go out on a limb and say we're not really there. Best pirate ship, chicken scratch. Yeah, we were accomplishing stuff. Little dirt never hurt. So, can we find a Hamiltonian cycle for this network? Oops. And I'll bump it over a little bit. Okay. Okay. So I can only go through a vertex once, right? These are the rules of the game. I can only go through a vertex once, but I can use the edges as often as I want. Sometimes it makes it hard, right? Because we can't get back to an edge unless we go through a vertex, so that's our only holdup. But let's see here, just kind of starting over here, what can I do? I can go down to here, and then I could go. So one problem that I'm seeing, I'm looking at this as a root, and my option would be to kind of go in a loop like this. That seems kind of boring, right? It's allowed, but it seems boring, right? And so let's see if we can do a little bit better. And let's do this outside root. Well, it puts me back at this vertex where I started, so it should be kind of over by then, but then I haven't touched on this vertex here. So what I'm gonna do is I'm gonna start here at, let's call it A, and let's do B, C, D. However you want to label them, it doesn't actually matter. So what I'm going to do, let's see if we can do this. Kind of a more fun cycle than just a loop, right? And so if I go from A to B, I'm just starting it out. What we decided was that, okay, well, if I go from A to B to D to B, or to A, then I miss out on C, right? So that's not an option. So if I go A to B to D to C, that's so boring, we're not gonna do that. So what if I try B to C? Right, so here's my first step, here's my second step. Now I'm at a crossroads again, right? And so if I go to A, well, then it's game over, but then I've missed out on D, right? So what I'm gonna do is I'm gonna go from C to D, and then voila. Because I have this roundabout way here, it worked out, right? So a Hamiltonian cycle would be something like, and what I just do is I just do A to B to C to D to A, right? Making sure that I only touch each vertex once, and I start where I end, or I end where I started. Okay. And let's see here. Did I bring it in or what? I did. Okay, nice. So I'm gonna steal this one. I think the problem became, so we don't actually need this handout for these ones here. We could have drawn them, but I needed it for this one, so I may as well do a couple more on there on the same page. Okay, so let's see here. If we have something like this, right, we're going to decide if each of the cycles that I give you are Hamiltonian or not. Decide if each cycle is Hamiltonian. That's not a question mark, question. All right, first one, A to B to C to D to A. Part B, other option, C to D to A to B to F to E to A. This one, right, the first one looks good to begin with, right? I'm at least starting at the same point that I'm ending. Here, I'm not even starting at the same point that I'm ending at, so it's out already, right? So you can use that as a method of elimination. And how about B to C to D to A to E to F to B? So here, I start at the same point that I end at, so that's good. But if I map it out, right, from A to B to C to D to A, I've made a loop, but I'm actually skipping E and F, right? So A, I'll do this. A does not include E and F. We just made a loop, which I said was kind of boring, right? So we don't want to do loops. Sometimes, I mean, there's solutions, but in this case, it's not a Hamiltonian cycle because we've left out E and F. So therefore, not Hamiltonian cycle. Let's do HC. Okay. How about for B? Well, we said we have to start and end at the same endpoint. So C and A starts at C, ends at A. Therefore, not a Hamiltonian cycle. How about for C? Well, I start at B and I end at B. And what I'm going to do is I'm just going to map this route out and make sure that I hit all the vertices and I only hit them once, right? You can look at the list, but sometimes it's a little bit hard to grasp. And so if I start at B and then I go to C and then I go to D and then A, and I can't see anymore, E to F to B, looks good, right? Starts and ends at the same point. All vertices are included only once, are included exactly once, I'll say. Therefore, it is a Hamiltonian cycle. Okay. Okay, so what I'm gonna do, just make a quick comment, and then we'll continue with this next day. So unlike Euler circuits, right, where we have the solution that we can lean on and that we can use to solve these problems, like I said before, a traveling salesman type of problem doesn't have a solution like that yet. But really fun article. That article that I found was from October 8th, 2020. So very, very recent work, which is really cool and really fun. So unlike Euler circuits, there is no solution. There is no solution to deciding whether a network has a Hamiltonian cycle. To deciding whether a network has a Hamiltonian cycle. Oops, I should capitalize it. This young prodigy. And recent development on the traveling salesman problem. Recent development on the traveling salesman problem can be found for the reader on Moodle. Can be found posted as a link on Moodle. Whee. I'm already dreading the review on Monday. All this, all these terms that we have to kind of refresh our memories on. But so what we're going to do is we're going to work through a traveling salesman problem next day, and we're going to look at some of the different solutions. So of course people have solutions, but no one has landed on an optimal solution. And so all right, so next day we'll work through it, a quick, or not a quick, it takes a while, but a traveling salesman problem, and then we'll move on to trees. So an Euler circuit does end on the same vertex. The Euler circuit, so to summarize, an Euler circuit, it ends on the same, so it's traversable if you're able to traverse the whole thing, touching each edge only once, right? The Euler circuit is a special case of that, where you start and end at the same point. And then the, each edge, nice, good. Yeah, so maybe kind of go through those definitions, because they're going to be a big, yeah, a big player here. Right, so traversable, and then Euler circuits are a special case of being traversable, and then Hamiltonian cycles refer to the vertices instead of the edges. Yeah, exactly. So the Euler cycle, or the Euler circuit, touches each edge and starts and ends at the same vertex. So it has that additional condition. Whereas if it's just traversable, you just touch each edge. And you can start and end anywhere. Nice. Nice work, guys. So pretty fun. Kind of problem solving, right? All right. Any other questions before I let you go? For the weekend, I guess. I know, it's only Wednesday. All right, I'll stop this recording here.